In this video, the heat transfer rate of composite cylinder is explained. The procedure that we are going to follow is similar to the procedure we already followed for the derivation of a composite wall or composite slab. Let us start the concept. Here, as shown in the diagram, we have a composite cylinder which is made up of two materials A and B. Two cylinders A and B are composite together to form a composite cylinder. As we discussed already, composite means combination of different materials, right? Here it is, the A and B are the different materials used to form a composite cylinder. Now it is a hollow cylinder, which means inside it is having no material. At the center it has no material, so it is a hollow cylinder. The inside of the cylinder, composite cylinder, having a hot fluid that is flowing, and the hot fluid has a temperature THF with a heat transfer coefficient HHF. Then the temperature of the first cylinder inside is a T1. Then at the interface between A and B is a T2. On the surface of B we have temperature T3. And the first cylinder's inner radius is R1. Then outer radius of the first cylinder or inner cylinder is R2, or that is also the inner radius of the outer cylinder. Then the outer cylinder's outer radius is R3. So R1 is inner radius of the inner cylinder, R2 is inner radius of outer cylinder or the outer radius of inner cylinder, R3 is outer radius of outer cylinder. The composite cylinder is placed in such a way that it is exposed to cold fluid at the exterior or at external surface. So HHF is the heat transfer coefficient of the cold fluid that flows over the composite cylinder. TCF is the temperature of the cold fluid. As it is made up of two different materials A and B, Ka and Kb are the thermal conductivities of those two different materials A and B, which constitute this composite cylinder. Now, the L is the length of the cylinder, which is invisible here, but actually it possesses some length L. Length of the cylinder is assumed to be capital L. Now, let us start the derivation. Before that, the heat start flowing radially outwards. The reason is the hot fluid present inside, cold fluid flows outside due to this temperature difference. As it is hot, here it is cold, due to which there will be some temperature gradient or temperature difference, due to which heat always start flowing from high temperature region to low temperature region, high temperature body to low temperature body. So now here the hot and cold temperatures exist, which causes the heat to flow always from high temperature to low temperature. Now the heat transfer takes place from hot fluid to cold fluid, right? Let us see the rate of heat transfer that is flowing through the composite cylinder. As inside we have hot fluid, the Q can be written as it is hot fluid. From the fluid the heat flows to a cylinder, right? So the interaction is now between a fluid and solid. The mode of heat transfer that exists now is convection. For convection, we have Newton's law of cooling, which has an equation for Q as Q is equal to HA delta T. So we are going to write Q as HA delta T. H is a HHF, hot fluid heat transfer coefficient. A is the surface area of the fluid that is flowing on which body? That is a cylinder. Cylinder surface area is a 2 pi RL. It is a 2 pi R1 into L. As up to this distance the heat transfer takes place, which is the inner radius of the inner cylinder. So 2 pi R1 into L. And the delta T is temperature difference, THF minus T1. THF is greater than T1, so THF minus T1. The same heat after flowing to the inner cylinder goes and flows through the inner cylinder. which means inside a solid the heat transfer takes place from one phase to another phase. The mode of heat transfer is conduction. For conduction, for the cylinder we already derived an equation in our previous last video, which has equation Q is equal to 2 pi kl into T1 minus T2 divided by log in R2 by R1. That was the equation we already derived. Right, go and refer if you have any doubt regarding that equation. So directly I'm using that equation. Q is equal to K 2 pi kl. K is a Ka for material A, as it is a material A, and this is material B. For material A, conduction Ka into 2 pi L into T1 minus T2. From T1 to T2 the heat transfer takes place now, divided by Ln R2 minus R1. Up to here it is R1, and then sorry, up to here it is R1, then this is R2. This is R2 and this is R1. So Ln R2 by R1. After flowing through body A or cylinder A, then it further goes and flows through cylinder B, which is again a solid. Inside the solid now heat transfer taking place, due to which the mode of heat transfer is conduction. Now for this conduction through a cylinder, again B is a cylinder again, so for the cylinder we have similar equation as like we had already. 2 pi kl into delta T by ln R2 by R1. The equation is modified with respect to the specifications we are having. Here's we are dealing with temperatures T3 and T2. So temperature T3 and T2 are used, and the radius are R2 and R3. So R3 by R2 is used. Clear? After flowing up to B, then it enters into cold fluid. Right? Now the heat transfer is in between a solid and a fluid. The mode of heat transfer between solid and fluid is convection again. For convection again we have equation HA delta T. That equation is modified with respect to the specifications we are having. H is HCF. We have a cold fluid heat transfer coefficient, cold fluid temperature. So with respect to them we modified the equation. Right, so Q is equal to HCF into 2 pi R3 into L, as up to this the radius is R3, L is the length, T3 minus TCF, from T3 to TCF for the heat transfer taking place. So HCF into 2 pi R3 into L into T3 minus TCF. So this is the rate of heat transfer, the same heat flowing from the center to outer surface. Now let us rearrange the terms in such a way that we have only temperatures. From let us say this is 1, this is 2, this is 3, this is 4. From equation 1 we can write a THF minus T1 as a Q by the remaining terms go towards LHS and go to denominator. THF minus T1 equal to Q by HHF into 2 pi R1 into L. Now consider these two. From equation 2, T1 minus T2 can be written as Q divided by this term, Q divided by Ka into 2 pi L divided by Ln R2 by R1. Right, now let us consider these two terms. Q is equal to Kb into 2 pi L into T2 minus T3 divided by Ln R3 by R2, from which T2 minus T3 can be written as Q divided by the remaining term. This is the term that is remaining, Kb into 2 pi L divided by Ln R3 by R2. And similarly from these two we can write a T3 minus TCF as a Q divided by the remaining term over here, HCF into 2 pi R3 into L. So these are the four temperatures temperature terms we got from the above heat equation. Now if we add all these four equations, this one, if we add all four equations, then minus t1 plus t1 get cancelled, minus t2 plus t2 get cancelled, minus t3 plus t3 get cancelled. We left with the THF and minus the TCF from LHS. On the right hand side, in all the equations we have Q common and 2 pi L common. Q and 2 pi L are common in right hand side of every equation. Now let us add all these four equations, then we got the equation like this. THF minus TCF that we remind with after cancelling all the temperature terms is equal to Q by 2 pi L is common from all the equations, and the leftovers are written over here. Clear? Now from this equation Q can be written as Q is equal to 2 pi L goes towards this and multiply with the THF minus TCF, and the rest of the terms are divided by the temperature term. So the equation will become like this. Q is equal to THF into 2 pi L divided by the whole term that present over here. Now these are the thermal resistance, we know that K by LA, right? Also, okay, let us simplify this. These equations can also be written as this. Ln R2 by R1 go towards this. 1 by A by B equal to B by A. That is the formula we used. 1 by A by B equal to B by A. Now we have this equation as final. Q is equal to 2 pi L into THF minus TCF divided by 1 by HF into R1 plus ln R2 by R1 divided by Ka plus log R3 by R2 divided by Kb plus 1 by HCF into R3. This is the equation for a composite cylinder which is surrounded by two fluids, hot and cold. Hot fluid flows inside the cylinder, composite cylinder, and having two different materials which make this composite cylinder. Let's move on from the equation we got finally. From this equation we can generalize this equation. If I have n such a type of cylinders which make the composite cylinder, if I have n cylinders, n concentric cylinders which are placed one over the other to form a composite cylinder, then the above equation is generalized in the sense like this. The numerator remains same as only one hot fluid is there, one cold fluid is there. On the denominator we may have a number of these terms, so all together they can be written like this: sigma n equal to 1 to n 1 by kn into ln Rn plus 1 divided by Rn. If you have 3 composite cylinders, then n is replaced with 1, 2 and 3. If you have 4, then n equal to 1, 2, 3, 4, like that. We are going to get 4 terms if we have 4 cylinders. We got 3 terms if we have 3 cylinders at this place. And these remain same. As one hot fluid is there, one cold fluid is there, so due to which the convection heat transfer takes place, the heat transfer coefficients remain same. So this is the equation, generalized equation. If we have no convection, here we have convection, so we got these HF and HF things, HF and CF things. If we have no such convection heat transfer, then if all the way this is only conduction, then in the conduction from T1 to some T3 the heat transfer takes place, and there is no such things, then we left with only the conduction terms. Then Q can be written as this: T1 Tn plus 1 divided by n equal to 1 to n. This is same. As many concentric cylinders we are having, those many we are going to write over here. This is the generalized equation for a concentric cylinder, right? So thank you.